Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. In this class, we will study central difference method. So, the outline of this lecture is we will discuss about methods of numerical analysis, finite difference technique, and in that central difference method we will discuss, and the algorithm for getting the time history of time history response of a building, that we will discuss today. So, methods of numerical analysis. So, we have discussed if a structure is given an input motion, either ground motion or say some motion force applied at the center of the mass, how do we get the solution of dynamic differential equation, that is dynamic equilibrium equation or equation of motion. So, we need to find out u, which is the response of the structure. So, for that various techniques are available. So, one method is method based on the interpolation of excitation function. In interpolation of excitation function, we divide the excitation into several parts and find the solution. So, that we have discussed in the previous classes, and in this class we will discuss about finite difference expression for velocity and acceleration, and the other techniques we are going to discuss in the subsequent lectures, that is methods based on assumed variation of acceleration. So, in this class we will discuss about the finite difference expression for velocity and acceleration and how we make use of that and find the solution of governing differential equation. The finite difference methods. So, in finite difference methods there are three kinds of finite difference methods. One is a forward difference. So, then the forward difference means what? We make use of the function value at I plus 1. So, if I is a time instant, we make use of I plus 1, and then in backward difference we make use of the one step before the time step given, and in central difference method we make use of both forward and backward. So, we evaluate the velocity and acceleration at a given point by making use of one step ahead and one step backward. So, how does it work? Let us discuss this. Like as you can see, the structure, idealized structure, single degree of freedom system is here. Mass is given, damping is given, and stiffness is given. So, inertia force, damping force and stiffness force, that combination is equal to the applied force. So, this is applied force. So, how do we get P? P of T is equal to minus m a, acceleration value is given. So, now we need to find out the response of the structure. So, how do we solve this one? Using numerical methods. Earlier we had discussed using classical method, and then Duhamel's integral approach or convolution integral approach, and then Fourier transform method. So, these three things we have discussed, and now we are discussing in the process of discussing this numerical method. In numerical methods we will be discussing central difference method. So, before going to the technique of central difference method, how does it work? Let me explain. So, if we take say a time instant, say tau, which is, you can see this is, it is in between Ti and Ti plus 1. So, if we want to get velocity or a displacement at this point, displacement at this point, displacement at this point 3. So, you can see this one. So, actually displacement is here and displacement is here. These are the displacement value. This is displacement function. So, at Ti, it is T is equal to Ti, displacement value is I. Actually, this is I. Okay. So, this one is I minus 1, this is I plus 1. So, I at I instant, u is equal to ui, at I minus 1 instant, u is equal to ui minus 1, and I plus 1, it is u equal to ui plus 1. Here in the middle of this, that means ui minus half, and here ui plus half. So, this is I minus 1 time instant, I time instant, I plus 1 time instant, and this is I minus half time instant, I plus half time instant. So, these 5 displacement values are available here. So, now velocity, that is u dot at I, that is equal to, so how do we get that? You can see this one, velocity at the displacement at this point divided by 2 delta t. This is delta t, this is delta t, so this is 2 delta t. So displacement velocity is nothing but rate of change of displacement. So this is change of displacement. So this value is u I plus 1, this value is u I minus 1. So this is change of displacement. So u I plus 1 is here, u I minus 1 is here, divided by the time interval between these 2 points, that is 2 delta t. So we can write the expression of velocity in terms of displacements. You can see this one, displacement. So where we are calculating velocity, we are calculating at I, and we are making use of one step ahead, that is u I plus 1 here, and next step one step backward, that is u I minus 1. Similarly, we get acceleration. Acceleration is rate of change of velocity. So we first calculate velocity at this point, velocity at this point, and the change in velocity divided by the time interval between them. If you can see here, velocity at u I dot I plus half here, velocity at this point. So we need velocity at this point, velocity at this point divided by this time interval. So that is delta t only. And now we already know how to find out the velocity at any time instant. So we substitute that in this one. So that is, you can see velocity at I plus half is this point. If we want velocity at this point, displacement of this point minus displacement of this point divided by delta. So you can see this one, displacement at this point is u I plus 1, displacement at this point is u I, and divided by delta t. Similarly, at this point, if we want to calculate velocity, we have to subtract this displacement minus this displacement divided by delta t. So you can clearly see this one, ui is here, ui minus 1 is here, and delta t is this. So this gives velocity at this point. Earlier one gives velocity at this point. Velocity at this point minus velocity at this point divided by time interval between them. So that is what is here. Now if we substitute this u dot I plus half minus u dot I minus half, these two expressions in this, and then simplify it, how it looks like, let us see. So I am substituting this here in place of this, and I am substituting this in place of this, divide. So you can see in this one, u I plus 1 remains. So now here u I minus ui. So here minus sign, here minus sign. So 2 ui, and this minus of minus plus ui minus 1, and then delta t is there common. So this will become delta t square. So as you can see here, u double dot I is equal to ui plus 1 minus 2 ui plus ui minus 1. So acceleration term can be represented by displacement at 3 points. Velocity term can be represented by displacement at 2 points. We wrote expression for velocity, expression for acceleration. So we have two expressions in terms of displacement. Now we will make use of this one in our governing differential equation. So assuming a time step at any time t is equal to ti at ith time step, mu double dot I plus cu dot I plus kui is equal to applied force at that time instant. So if we substitute, we already know that velocity can be represented in terms of displacement, acceleration also can be represented in terms of displacement. We substitute velocity value and acceleration value in this equation and simplify it further. So substituting that, as you can see this one, mu I plus 1 minus 2 ui plus ui minus 1 by delta t square, acceleration term we substituted, velocity term we substituted, and displacement term is ui is equal to pi. Now in this one, how many different terms are there, different displacement values are there. So ui plus 1 is one displacement, ui is another displacement, ui minus 1 is another displacement. So we have 3 displacements in this. So we have 3 displacements in this one. So if we simplify that in terms of the displacements, so what we get is, you can see ui plus 1 is here and ui plus 1 is here. So that means mass divided by delta t square will come here, and then c divided by 2 delta t will come here. So, that will give us the coefficient for ui plus 1. We are sending all these things to right hand side, that is pi minus ui term. If I look at it, kui is here, and in this one we have another ui term. So, when it goes that side, it becomes minus k minus, that is 2m by delta t square into ui. And then similarly ui minus 1 term will come from this, one term will come from this one, another term will come from this one. So, that is in this one m by delta t square term is here, and here c by 2 delta t term is here. So, now we have expression rearranged in the form of ui plus 1, ui minus 1, ui. So, again this expression can be simplified, and if we rewrite it, all this one is a force term. You can see this one. So, pi minus m by delta t square minus c by 2 delta t into ui minus 1 minus k 2m by delta t square into u. This is force term. And then k value. So, k value is this one, you can see m by delta t square, c by 2 delta t, this is. So, this entire expression can be written in simple form, that is k cap into ui plus 1 is equal to pi cap. So, this entire expression is pi cap and this expression is u. So, in this one we can clearly observe that for getting displacement at I plus 1th step, that is forward step, next step, we need pi of that term. Displacement is dependent on displacement of that term and the previous term. You can see this. So, unknown displacement ui plus 1 is found out by displacement at I and displacement at I minus 1 without using equation of motion at I plus 1th time step. So, that is the beauty of this central difference method. Without using expression, equilibrium equation expression for at time instant I plus 1, we are getting this. Now, how does it happen? It happens by initial values. So, the initial displacement ui in place of I minus 1. So, this is a fictitious term because time starts at 0, but we need one displacement at negative time, and then I minus 1 is required. These things are required for finding ui. So, if we look at ui, u dot I velocity, ui plus 1 minus ui minus 1 by 2 delta t. Then if we want at 0, u0, so I is equal, if we put I is equal to 0, u dot 0. So, if I is equal to 0, that will become u1. If I is equal to 0, that will become minus 1. So, that means what? We need displacement at minus time instant, that means before 0 term. So, this is a fictitious velocity, a displacement term we need to find out. We will discuss about how to find it out. Then acceleration. Acceleration value is ui plus 1 minus 2 ui plus ui minus 1 by delta t square. This is acceleration term in terms of displacements. Then that one, if you want initial acceleration, you put u double dot 0 at time instant 0. So, then you will get u1, you will get here u0, you will get here u minus 1. So, u0 can be initial condition, that is initial displacement. If you define initial displacement, u0 can be there, and then u1 we need to find out. So, what we do is to find it out, solving for u1 is unknown here, solving for u1 in this equation and substitute that u1 value in the second equation. So, if you substitute that, solve for this one and substitute in the second equation, we get u minus 1 term, that is u0, that is initial displacement, initial velocity, and delta t square by 2 into initial acceleration. So, we know initial displacement and initial velocity, but how about initial acceleration? So, for finding initial acceleration at time I is equal to 0, if u0 is 0 and u dot 0 is 0, before the start of vibration, initial displacement is also 0, initial velocity is also 0. So, both are zeros. So, if you take the equation of motion at 0th time, so that is mu double dot 0 plus c u dot 0 plus k u 0 is equal to p0. So, from this we can find out initial acceleration. So, that initial acceleration is like this p naught, this is minus sign, minus C0, this is minus sign. Okay, P0 minus Cu dot minus Ku divided by M. So we get U double dot 0 from this. So once we get U double dot 0 from this, you substitute here. Then initial displacement you substitute, initial velocity you substitute, then you get a fictitious displacement term. So now to start the process of getting, because this Pi is known to us, so how to start the process? Let's see. The algorithm for that is initial calculations we do. Actually, let me explain first. This is a force given to us. So this can be written in terms of a table P at I, P. So I is equal to 0, P is at force at P is equal to 0, this one. I is equal to, I means time instants, these are time instant, different time instant, we have all force values defined, say 0.01, 0.02, the Ti. I is a time instant, so 0, 1, 2 like that. So now we need to find out the parameters and finally displacement, velocity at that, acceleration at I. So these things we need to find out. So now how do we go about initial calculations? From the given system, so we know already P value, so P0 value we know, damping value is given in the system, and stiffness value is given in the system. Initial velocity we assume, initial displacement we assume, we get initial acceleration. From initial acceleration we get the fictitious displacement term U minus 1 term. Then once we have that, then we find out K, M by delta T square, C by 2 delta T. Delta T is this time instant, this is delta T. Okay, it can be fixed, though it need not be fixed value at every time, but for convenience sake we fix it. And then A is this, B is this value, this is further simplification in terms of P, and then P cap we get that for that time instant. So Pi minus A Ui minus 1 B Ui, P cap I is equal to Pi minus A Ui minus 1 B Ui. So this Pi will come from this column. Okay, whatever is ith step, that P we will substitute here, and then Ui minus 1 we will calculate and put it. Then Ui plus 1 is equal to P cap I by K cap. So K cap we calculated, P cap we calculated, we get displacement. So once we get this initial displacement, initial velocity is 0. Once we get displacement, we write these values here. And then through that we calculate velocity, and calculate velocity we write here. So these columns will be filled. And then we derive acceleration, we write acceleration here. So like that these columns are populated. In summary, what we have discussed in this class. In this class we have discussed about central difference method. So equation of motion, which is mu double dot cu dot plus ku is equal to P. So in numerical methods we calculate this at every time instant. So mu double dot of ith step plus cu dot of ith step and ku of ith step is equal to P of ith step. Velocity and acceleration we represented in terms of displacement using central difference method. So these two expressions of velocity and acceleration we substituted in the governing differential equation to get a equation. So then we could see in that equation that ui plus 1, that is displacement at time I plus 1, is dependent on the previous displacement values only, not the forward or that time instant. So in that manner we can calculate displacement time history. So I can vary from say 0 to n time step as long as the forcing function is there. So as long as that I can vary say 0 to 1, 2, 3, 4 like that. So we can calculate displacement, velocity and acceleration at all those time instant. And an example problem will be shown in tutorial of this class.